Hey everyone, we are in chapter 5. We have just started it. We've talked about the 11 fundamental identities, which are the 6 reciprocal identities, the 2 ratio identities, and the 3 Pythagorean. And we've already discussed out of these 11 identities that you need to memorize. You've already known 8 of them since the beginning of the course. We just knew these in terms of X, Y, and R, or opposite, adjacent, hypotenuse. Now we're just writing the trig words, the trig of functions that relate. So really the only 3 identities that are new to you that you have to memorize are the Pythagorean. Okay, in 5.1 we use these identities for 2 purposes. Number 1, we saw another way to evaluate a trig expression. And then secondly, more importantly, we saw we could take these trig identities and use them for simplification purposes to follow order of operations. In section 5.2, we're going to continue on this path of using these trig identities to simplify algebraic expressions. But this is a little bit easier than 5.1 because you know what the answer is going to equal. So for example, in your notes, example 1, it says cotangent theta divided by cosecant theta equals cosine theta. They want you to verify that the left side does equal the right side. So this is easy because you know what the answer needs to come out to be. You know when you're done working in the left side, you should have cosine theta. So that's why everybody likes section 5.2 a lot better. My think about this section is it's all about the algebra, showing all the steps, how you take one side of the equation and get it to equal the other side. So the first rule is only work with one side. You're not to work with both sides. You pick the most complicated side, which is usually the left, and you work it down following order of operations to get to the right side, to show that it balances. In order to do this, you're going to be applying your identities, doing some substitution, as well as reviewing your algebra skills. So there's a lot involved here, but at least in 5.2, you know what your answer has to come out to equal, unlike in 5.1 where you didn't have a clue. All right, so let's start. I want to make cotangent theta divided by cosecant theta to become cosine theta. In trigonometry, lowest terms means changing all the trig functions in terms of sine and cosine. That's what lowest terms means. So if I have cotangent theta here and I go to my identities, under reciprocal, cotangent theta can be replaced with 1 over tangent theta. But we don't want to use this because every time we're doing a simplification in trig, we want to get our answer in terms of sines and cosines. So let's not use this identity. We also know with the ratio identities, cotangent theta can be replaced with cosine theta over sine theta. So that's what I'm going to do. I'm going to make that first substitution. I'm going to replace cotangent theta with what it equals, which is cosine theta over sine theta. Remember, do not forget to write the thetas. If you do, it's technically wrong. Divided by, now I got to replace cosecant theta. Well, cosecant theta, according to the reciprocal, is 1 over sine theta. So I'm going to do my substitution here. You bring down the right side. You don't lose it. You just bring it down. We're not going to do anything to the right side, but we're going to bring it down each step to show that we're verifying. We're going to show that the 2 sides equal. This is kind of like balancing your checkbook, showing that your debits and credits equal out. Now, on the left side, we have a fraction divided by a fraction. We know there is no such thing as dividing by fractions. You multiply by the reciprocal. So I will write cosine theta over sine theta times the reciprocal of the denominator, which is sine theta over 1. What happens here is now we're multiplying. Now we discussed this yesterday in the last video. We're multiplying and these bars mean to divide. So does that mean you have to multiply first and then divide? Or can you do the opposite and divide first and then multiply? Because multiplication and division are equal, mom and dad are equal, according to order of operations, it's always easier to divide first. So what's in the numerator and the denominator that can divide out? Correct, sine theta. Sine theta divided by sine theta is 1. Just like 3 divided by 3 is 1. X divided by x is 1. So what you're left with is cosine theta over 1. And we know any term divided by 1 is itself, and we get cosine theta equals cosine theta. Check. That verified. You proved to me the left side can become the right side. Pretty neat, right? Not hard, just reviewing algebra and using our identities. Okay, in your notes, let's go to example 3. So I'm going to erase this. And example 3 is verify that cosine squared theta, parentheses, tangent squared theta, plus 1 would equal 1. Okay? Now, there's technically 2 ways to work this on the left side, to work this expression. Either way is correct, just one is faster than the other. So if we follow our rules, please excuse my dear Aunt Sally. P means always do what's inside a grouping symbol first. So that's the way I'm going to proceed. I'm going to look inside here and say, oh, there's tangent squared theta plus 1. Ding dong. Let me think about that. I got a square and a 1. Let me go look at my Pythagoreans. Is this one of my Pythagorean identities? Sure enough, it is. 1 plus tangent squared equals secant squared theta. Well, if I write tangent squared theta plus 1, or 1 plus tangent squared theta, according to the commutative property of addition, it doesn't matter what order I write the terms in. Tangent squared theta plus 1 means the same thing as 1 plus tangent squared theta. So I can now substitute what's inside my parentheses with secant squared theta. So I'm going to do that. Now we have cosine squared theta and secant squared theta that are connected by multiplication. Well, what is the relationships at the beginning of the semester between cosine and secant? That's correct. They're reciprocals of each other. And in 5.1 we discussed this. What do you know from arithmetic? What happens when you multiply reciprocals? If I multiply 2/3 times 3/2, I get 6 over 6, which happens to be 1. So the rule is, from arithmetic, when you multiply reciprocals, you always get 1. If that's the rule in arithmetic, it's the rule in algebra. If I take x and multiply it by 1 over x, the x's cancel, I get 1. Well, if that's the rule in algebra, that is also the rule in trigonometry. If we multiply reciprocals, our value is 1. Now, how many cosines are here? There are 2 because it's squared. How many secants are here? There are 2. There's a squared. So if you think about this, what you're saying here is there's a cosine theta times a cosine theta times a secant theta times a secant theta. Correct? And we know if we multiply reciprocals, our value is 1. And we know if we multiply these 2 reciprocals, our value is 1. So we'll get 1 equals 1. We verified. Everybody's okay with that? Yeah, that's one approach. Let's try it another way. Okay? Suppose you didn't realize inside the parentheses was a Pythagorean identity. Then what you would look and say, oh, I have a monomial, a term on the outside of the parentheses, and that always means to distribute. So another approach here would be distribute. So this would become cosine squared theta times tangent squared theta, and this would become plus cosine squared theta equals 1. Now, I don't want to do anything with the cosine because, again, that's lowest terms. But I can replace tangent squared theta. Now, the choice is, what do I replace it with? Do I replace tangent with the reciprocal 1 over cotangent? Do I replace tangent with sine over cosine? Yes. That would be considered lowest terms. So we're going to leave our cosine squared theta, and we're going to replace tangent with sine over cosine. But because this is tangent squared, which means tangent times tangent, this would be sine squared, and this would be cosine squared. Okay? Now we're multiplying fractions. I'm going to put a 1 over here so I can see it. We know the rule is multiplying fractions is no problem. Top times top, bottom times bottom. However, we know because this is multiply and the bars are divide, why don't we divide first? What you should notice is I have a cosine squared in the numerator, a cosine squared in the denominator, so they're going to divide out and make 1. So that's going to leave me sine squared theta over 1, which we don't need to put the 1, plus cosine squared theta. Well, if you look at that, that's sine squared plus cosine squared. That's a Pythagorean identity. And according to the rule, sine squared plus cosine squared would be 1. 1 equals 1. So there's 2 different ways to verify that identity. Neither way is right, neither way is wrong. You just got to show all your algebra steps. Okay, let's try another one in the notes. Okay, let's look at example 4. Sine theta minus cosine theta over sine theta equals 1 minus cotangent theta. Again, we're going to verify, we're going to work with the left side because that's the messier side. It's the fraction. So there's a couple of operations going on. First operation I see is subtraction. Well, can you subtract a sine from a cosine? No, they're not like terms. That would be like you trying to subtract x and y in algebra. It doesn't work. Well, now I see division. Here's the boo-boo you all are going to make. You all are going to say, oh, sine divided by sine is 1, and cancel those out. But you got to remember, guys, let's go back and relate this to arithmetic. If I had an arithmetic, 3 plus 5 over 2. Okay? 3 plus 5 over 2. Normally, the way a 3rd and 4th grader would work this is they would add the numerator, they would get 8, and divide it all by 2 and get 4, right? So we all must agree the answer here is 4. But when you have this divide by 2, when you have a monomial in the denominator, when you say who am I dividing by 2, you're not dividing the first term by 2. You're not dividing the second term by 2. Because that bar goes all the way across, you're dividing both of them by 2. So this could be rewritten as, let me take 3 and divide it by 2. Let me take 5 and divide it by 2. This expression in arithmetic means the same thing as this. Now we can do this in our head. Let's think of money. $3 divided among 2 kids would be $1.50. $5 divided among 2 kids would be $2.50. And if I add $1.50 and $2.50, don't I also get 4? Yes. So the rule is here is when you have a division bar and you have a monomial in the denominator, you are dividing this monomial into all the terms in the numerator. So the biggest mistake you guys make is you just divide the sine theta by sine theta. You need to break this and show you're dividing sine theta into both terms. So that's what we need to do. We need to rewrite this as sine theta over sine theta minus cosine theta over sine theta. And we'll leave the right side. Well, what do we know about something divided by itself? A term divided by itself is 1. What do we know about cosine theta over sine theta? Well, that is our ratio identity. Cosine theta over sine theta is cotangent theta. And now you have verified. This last step is important to show the left side is equal to the right side. It's like doing a check for an equation, showing the balance. Is everybody okay? All right, let's try another one in the notes. Let's look at example 5, because now it gets a little bit more messier. Okay. Example 5 in the notes says, I have 1 plus 2 sine theta cosine theta. And it's over sine theta plus cosine theta squared. And it wants me to verify that it equals 1. That's what it's asking me to do. Convert this left side into this right side. All right. In the numerator, I see addition. Can I add this 1 to this 2 and make 3? No, because it's not 1 plus 2. It's 1 plus all of that expression. That would be like me asking you to add 1 plus 2x. You can't do it. So there's nothing we can do in the numerator. I'm going to leave the numerator alone. Denominator says square. What does squaring mean since elementary school? Squaring means to multiply it by itself. So we all know if I say 3 squared, it's 3 times 3, which is 9. So if I say sine x plus cosine x squared, I am saying for you to multiply sine x plus cosine x times sine x plus cosine x. That's what it means. You need to write it twice so you don't make a careless error, because you should all know there are two terms in this parentheses, there are two terms in this parentheses. That means these are called binomials. The only way to multiply binomials in algebra is to do the distributive property FOIL. So we're going to use our FOIL skills. So again, I'm going to leave the numerator alone because I'm not touching that. I'm working in the denominator. I'm about to FOIL. What does FOIL stand for? First, outer, inner, last. It's a pattern, a way to make sure you distribute every term to every term. So who is first? Sine theta times sine theta. Doing that is the same thing as multiplying x times x. So in algebra, we all know x times x is x squared. So sine theta times sine theta would be sine squared theta. That's how you write it. Outers. Okay, that was the first. Outers, sine theta times a positive cosine theta. Well, it would be positive. You cannot do anything with sine theta and cosine theta. That's like multiplying x times y. So in algebra, if I ask you to multiply x times y, you write xy. So if I'm asking you to multiply sine theta times cosine theta, you just write sine theta, cosine theta. They're side by side, so I did multiplication. I is my inners, positive cosine theta times sine theta, so we're going to have a positive. Cosine theta times sine theta is exactly what I just said. Cosine theta, sine theta. And then finally, we got to do our last. Our last are going to be cosine theta times cosine theta, which is cosine squared theta. And that all equals 1 still. So we're trying to get this to become 1. Well, you guys know when you do FOIL, first, outer, inner, last, the outers and the inners should combine. Either they'll cancel, because one's positive and one's negative, or you'll be able to add them up. So let's look at our outers and inners. Sine theta, cosine theta, plus cosine theta, sine theta. Now somebody's going to tell me, well, Ms. Black, they're not like terms. Sure they are. Think about algebra, and that's the whole purpose of this chapter, to relate the trig expressions to algebra. If I wrote in algebra, xy plus yx. We all know in algebra, when we're writing terms connected by multiplication, we put them in alphabetical order. So xy is in the correct order. But in algebra, we don't ever write yx, because yx means the same thing as xy. So this is really asking you to add xy plus xy, which means I have 2 of these xy's. 1 plus 1 makes 2. We know we could change the order of yx and write it as xy, because that's your 3rd grade rule, commutative property of multiplication. From 3rd grade, if I say 3 times 2 and you say 2 times 3, we both get a 6. So in algebra, if you say xy and I say yx, it means the same thing. Which means in trig, if you say sine cosine and I say cosine sine, it means the same thing. Now, if it helps you and you want to rewrite this both in the correct order, if you want to rewrite this as sine theta, cosine theta, I'm okay with that. So you can see they're both the same. But if they're both the same, one of these and one of these makes 2 of those terms. So now I have, again, the numerator staying. Bring the numerator down. Don't lose your work. But now the denominator is going to have sine squared theta plus 2 of these. So 2 sine theta cosine theta plus cosine squared theta. And we're trying to get it to equal 1. Y'all with me? I'm looking for the process. Don't you dare tell me you're going to look at this and know it equals this. That's not the purpose of this chapter, of this section. It's to show me you know how to do algebra. Okay, now, if you look closely, we're still not done with the denominator. We're close. See, in the numerator, we have 2 sine theta cosine theta, and in the denominator, we have the 2 sine theta cosine theta. That's good. Now, in the denominator, we have sine squared plus cosine squared. Well, isn't that a Pythagorean identity? And doesn't it equal 1? If you want, you can rearrange the order. You could rewrite the denominator as sine squared theta plus cosine squared theta plus 2 sine theta cosine theta. But I don't expect you to rearrange it on paper. What I expect you to do is, you know, you can't do anything with the numerator. But in the denominator, you know sine squared plus cosine squared is the Pythagorean, and I could take out these two terms and replace them with 1. And now I have in the denominator 1 plus 2 sine theta cosine theta. Well, will that equal 1? Well, if you look, in the numerator we have 2 terms, in the denominator we have 2 terms, and we're dividing the exact same thing. So from 3rd grade math, when you divide the same exact number, 8 divided by 8, you get 1. When you divide negative 8 divided by negative 8, you get 1. So in algebra, if this binomial is exactly like this binomial and you divide it, you get 1. 1 equals 1. The key here is to understand I'm looking for the algebra. I'm looking for the step-by-step process of how you're using your algebra skills to verify. Okay, in your notes, we're going to do one more example that I think we need to go over as a group. And that is example 8. Okay. 8 is cosine theta over 1 minus cosine squared theta minus 1 over 1 minus cosine theta equals negative cosecant squared theta. Okay. All right, guys. So again, our job is to verify. Normally speaking, it's the left side that's the messy side, the ugly side, and we're trying to get it to be the right side. We're not moving anything, we're verifying, we're doing a balance. So I got to prove that this left side will come out to be negative cosecant squared theta. Well, the first thing I notice on the left side is I have fractions. 1 fraction, 2 fractions. And I notice they're connected by what operation? Subtraction. So we know from 3rd grade math to add and subtract fractions, you need a common denominator. This denominator is 1 minus cosine squared. This denominator is 1 minus cosine. So they're not the same denominator. Now, I know the problem is you're going, oh my gosh, how am I going to do this? Look at me. If it confuses you that the trig expression is in there, take it out, go to the side, and think about this in terms of algebra X. So I'm going to go over here to the side for a minute and show you how I think about this. This scares me, 1 minus cosine squared theta. So in that denominator is a 1, a minus. But instead of writing cosine squared theta, I'm just going to call that x squared. I'm going to replace x for cosine theta. So that's 1 minus x squared. This denominator is 1 minus, and cosine theta is just x. There's no square in this one. So let's take this back to algebra. If I had the denominator 1 minus x squared and 1 minus x, and I wanted the least common denominator, one of the basic things you should have learned in algebra is to find the least common denominator. All the denominators have to be in lowest terms, which means they all have to be factored. Okay, I know it blows your mind, but that's the rule from 3rd grade arithmetic. To find a least common denominator, you have to factor. You have to get the denominators breaking down in lowest terms. So, guys, can we factor 1 minus x squared? Sure. That is a difference of perfect squares. And that factors to be 1 times 1. X squared is x times x. 1 gets a plus, 1 gets a minus. So that denominator is not in lowest terms. It needs to be factored. What about the denominator 1 minus x? Is it in lowest terms? Well, does it factor? Let's go through the rules of factoring. Do we have a GCF? Well, the only thing we can divide a 1 and an x by is a 1, and that's not going to change it. Is this a difference of perfect squares? No, because x is not a perfect square. Is it a trinomial, 3 terms? No. So you know that that denominator is in lowest terms. So now to get the LCD, the rule is you take the most of every prime piece. Not all of the prime pieces. So a lot of mistakes are made because you guys think the LCD is all 3 of these parentheses. It's not. The LCD is the most of each different piece. I have a 1 plus x. I don't have a 1 plus x. I need the most, so I need 1 for my LCD. This has a 1 minus x. This denominator has a 1 minus x. They each have the same amount, so I need one of those. So your common denominator would be 1 plus x, 1 minus x. Now the same thing is true in trig. These denominators are not the same. You cannot just go stick a square up there. That's mathematically illegal. So again, to find a common denominator, you have to make sure these denominators are in lowest terms. This one is not. 1 minus cosine squared x is a difference of perfect squares. This can be factored to be 1 times 1 cosine theta times cosine theta. 1 gets a plus, 1 gets a minus. Now that's gone. This denominator, 1 minus cosine x, is in lowest terms. The GCF is 1, so if you pull out a 1, it's not going to change. It's not a difference of perfect squares, because even though that's a difference and that's a perfect square 1, you can't multiply the same thing to get cosine theta. It's not 3 terms of trinomial, so this denominator is in lowest terms. So now if I look closely, what is the common denominator between 1 plus cosine theta, 1 minus cosine theta, and 1 minus cosine theta? I need every prime piece. So I need the 1 plus cosine theta. And then because this denominator has one of these 1 minus cosine thetas, and this denominator has one of these 1 minus cosine thetas, I need one of those. So this would be our new denominator. And I'm going to write it just like you learned in algebra. And you learned in algebra, if you change the denominator, you must change the numerator. We all know if we change 1/2 to fourths, to get the 1/2 to become fourths, you had to multiply by 2. That's why 1/2 is 2 fourths. So guys, look, this denominator is the same. So my numerator is going to say cosine theta. This denominator is different. It started out in the denominator with 1 minus cosine theta, where that's there, but then we got the 1 plus cosine theta. How are these connected? Multiplication. So if I multiply the denominator by 1 plus cosine theta, I have to multiply the numerator by 1 plus cosine theta. So if I multiply this out, negative 1 times that is all of that. Or you can leave the negative in the middle and just multiply by 1 right now. Okay, so there we go. There's our new denominators. There's our new numerators. Now, the whole purpose of making common denominators is to make this one fraction. So I'm going to make one fraction bar. I'm going to put down my denominator again, my LCD. And now I'm going to do what this says. It says to take cosine theta and subtract from it 1 plus cosine theta. Here's the next boo-boo. This is subtract. Subtract means you always change the signs. So that's not really a 1. If we're going to subtract it, it becomes a negative 1. That's not really a cosine theta. If we're going to subtract it, it becomes a negative cosine theta. Okay, we'll bring down our right side because it's not changing. So it doesn't matter to me if right here when you're multiplying, if you multiply by negative 1 and change the signs right away, or you leave it as subtraction and then you multiply by it and change the signs. What you'll notice is in the numerators, what happens with cosine theta minus cosine theta? Well, that makes 0. That cancels, right? So now you have negative 1 over 1 plus cosine theta, 1 minus cosine theta. And it still equals negative cosecant squared theta. Well, I'm getting close. This answer has a negative. I have a negative in my fraction. Now you're going to say, how does this fraction become this monomial? Well, let's think. Fractions can flip reciprocals, right? And we know for cosecant, the reciprocal would be sine. So maybe if we can get this become a sine in the denominator, then we would have our reciprocal. Well, how are we going to get a sine out of here? There's nothing to substitute for. Cosine is lowest terms. Cosine is lowest terms. Everybody think. These are parentheses. So what operation is that? Very good. That's multiplication. So now let's multiply this back out by FOIL and see what happens. Okay, so I'm going to go over here. We have a negative 1 in the numerator. We're going to do FOIL. First, 1 times 1 is 1. Outers, 1 times negative cosine theta is negative cosine theta. Inners, positive cosine theta times 1, positive cosine theta. Last, positive cosine theta times negative cosine theta. Well, a positive times a negative is a negative, and cosine times cosine is cosine squared theta. All right? We know when we do FOIL, we have 4 terms, and if you look, the inners, negative cosine theta, and the outers, positive cosine theta, will cancel. They'll make 0. So now you have negative 1 over 1 minus cosine squared theta. Well, I got a 1 and a square. I'm thinking that's a Pythagorean identity. Let's go over here. Remember we talked about this. All these Pythagorean identities can be manipulated. How do I take this Pythagorean identity and get it to look like 1 minus cosine squared? I would take the cosine squared and move it to the right, and that I would move by subtraction. So if I move that cosine squared theta over, I would have 1 minus cosine squared, and it can get replaced with what it equals, which is sine squared. So now this becomes negative 1 over sine squared theta. And we know the reciprocal of sine is cosecant. Because that's sine squared, the reciprocal of that would be cosecant squared. Because there's a negative there, we just verified. Negative cosecant squared theta equals negative cosecant squared theta. So that was a tough one, because it took a lot of thinking about your algebra skills. These are not easy by no means, I get it. But it's reviewing all your algebra skills we're going to need. So take your time. The most important thing to understand is, first of all, only work with one side. The side that's more complicated is the side you work with. Do not try to move things back and forth. The right side stays put. You don't touch it. You work with the left side. You're using all your algebra skills, as well as you're trying to find identities that you could substitute in for. I hope you have fun with this section. See you in the next video.